We talked about the importance of scaffolds, and one of the properties that I mentioned was mechanical properties. Imagine that you made a scaffold and you want to use it in a biological system. After implantation, it would experience various forces in different directions, and as a result, it shows different behaviors with respect to its mechanical properties. For example, a scaffold can be rigid, which makes it suitable for bone tissue engineering, or it can be soft and elastic, which is perfect for soft tissue repairs like muscles or nerve tissues. In addition, the cells can feel the mechanical properties through cell biomaterial interactions and behave in a certain way. For example, some degree of elasticity would stimulate the proliferation or differentiation of the stem cells. Therefore, measuring the mechanical properties of our scaffold is essential in our design. If we apply external forces to the scaffold, its molecules develop internal forces in the opposite direction to resist these applied forces. We call this mechanical stress, which is distributed over the entire surface of the cross-section. So a stress is a measure of force per unit area, and its unit would be Newton per square meter or Pascal. We can apply various types of forces to our scaffold, and they can create different mechanical stress. We can pull or compress the scaffold, which is called tensile and compressive stress respectively. They're called normal stress because the force we apply is perpendicular to the cross-section. However, the force can be parallel to the cross-section, which is called shear stress. Some stresses can be more complex when you bend or twist your scaffold, which we're gonna talk about at another time. As you can see, the stress can cause deformation in our scaffold. For example, under normal stress, the length of our scaffold would change. We can describe this deformation with a strain, which is equal to the length after deformation divided by the original length. So how do we use these concepts to understand the physical behavior in the lab? One lab equipment is called a universal testing machine, or UTM. It has two grips which you can put your scaffold between them, and it applies force to the material. During the test, it gives you the stress-to-strain curve, which is typically like this. At first, as you increase the force, the deformation increases with a linear relationship between a stress and a strain. So if you remove the force, the material returns to its original shape and size. That's what we call elasticity, and we call this region elastic region. The yield point is the end of the elastic region and the beginning of the plastic region. In the plastic region, materials show plastic behavior and experience non-reversible deformation. Since we don't want our scaffold to deform permanently in the biological system, biomaterial behavior in the elastic region is very important. We can see the elasticity when we work with a spring. Based on Robert Hooke's law, the force required to deform elastic objects should be directly proportional to the distance of deformation, regardless of how large that distance becomes. But if you change the spring, you find that if you apply the same force, the distance would be different because some springs would show more resistance, which is shown with K in Hooke's law. Since the stress and strain are proportional to each other in the elastic region, if we divide these two, we can find a constant value, which is called the Young modulus or elastic modulus. If I rearrange this formula, you can see the resistance here. So we can conclude that the resistance is equal to the Young modulus multiplied by the cross-section divided by the length of the material. This resistance of deformation when a force is applied to a material is called a stiffness. Now with three different components, we can measure the stiffness of the material. The Young modulus shows the intrinsic elasticity, which is different in various materials. For example, all rubbers in the world have a Young modulus of 0.01 to 0.1 gigapascal, and all steels have a Young modulus of 200 gigapascal. So with the same cross-section area and length, the steel has a higher stiffness compared to rubber. In contrast to Young modulus, stiffness is an extrinsic property, which is not essential or inherent to the material. Imagine another rubber with a higher length and lower cross-section area. Since they have the same Young modulus, the stiffness of this rubber is higher. Therefore, when you design a scaffold in the lab, you should pay attention to the Young modulus of the biomaterial that you use, the cross-section area of your scaffold, and the length of your scaffold.